All right. So on these notes here, standard 40, properties of limits. Go ahead and scroll down to the bottom question there. Relationship between continuity and the existence of a limit. Briefly just talked about this. Talked about it a little bit last class. Here's the relationship. Yeah. If a function is continuous, then the limit exists. This could be true of the entire function being continuous, meaning there's no holes, jumps, asymptotes in the function at all, in which case this is saying the limit exists at every point. Or this could be just talking about at one point. If there's no asymptote, hole, or jump at a single point, then the limit exists at that point as well. So this could be, again, big picture or just a small window. So I'll change this to say at a point. The limit exists at that point. But what this Venn diagram also means is that there are plenty of functions that are not continuous where the limit still exists. And the example that we talked about is when there's a hole in the graph. That's one example. When there's a hole in the graph, the function is not continuous. The limit exists at that point. Remember that continuous means that the graph is one piece, that there's no breaks or jumps or gaps in it. Actually, what continuous means, here's the real definition. So what it means for f of x to be continuous at some random point c. That is true if the limit of f of x as x approaches c equals the y coordinate at that c. That's what continuity actually means. So this is like the math way to say it. This is like just the normal way to say it. The limit is the same as the y. Okay. So what this means is that if a function is continuous at whatever point we're talking about, all we need is the y coordinate, and that is going to be the limit. So some of these problems are going to be very, very easy. For example, number one here, the line y equals 3. What does that look like?
Just a line at 3.
A line at 3? What do you mean? Kind of line?
What's that? Okay. It's not like it's a vertical line.
Vertical line?
Or it's a horizontal line, and it's a it's a horizontal line at 3 on the y-axis.
Yeah. Yes, horizontal line at y equals 3. Is that continuous? Yes, it is. So the limit as x approaches 1 is going to be the same as the y coordinate at 1. what is the y-coordinate of the line y equals 3 at any point, but also at 1. 3. It's 3. It's 3 at all points, but also at x equals 1. Okay, the line y equals x, what does that look like? This, yeah. Is that continuous?
Yes.
Yes. Which means the limit as x approaches -4 is also going to just be the y-coordinate as x approaches -4, which would be -4. Yeah, we just plug in -4 for x. 4x squared plus 3, what does that look like? Parabola. Is that continuous? Yeah. So the limit is just going to be the y-coordinate. Take 1, you plug it in, you find the y-coordinate. What's the y-coordinate? 7. So it's really, really easy when the function is continuous. You just plug in x, you get y, and that's the limit. It's also the value, it's the y value, and it's the limit at the same time. Number 4. Is number 4 continuous? No. What type of discontinuity are we going to have in number 4? We're going to have a vertical asymptote when the bottom equals 0. What value of x would give us a vertical asymptote? 1? What's that? What's my number 1 rule in math? What am I not allowed to do?
0.
Yeah, bottom can't equal 0. Okay, solving for that, I add 2 to both sides. X cubed equals 2. How would I get x by itself?
Squared.
Cube root, both sides. Yep, so x cannot equal the cube root of 2. Do we agree? We'll have a vertical asymptote at cube root of 2. Do we agree? Okay, otherwise known as the infinite discontinuity. Is that the point that we're trying to find the limits at? No. What x value are we trying to find the limit at? 1. Okay. X is not allowed to be cube root of 2. We're not asking about cube root of 2. We're asking about 1. This graph is continuous at x equals 1. How do I know that? Because there's nothing in the denominator that would be 0 if I plugged in 1 for x. So I can plug in 1 for x and just get the y-coordinate, and that's the limit. So 2 times 1 minus 1 over 1 cubed minus 2. We just get -1. So again, we're not asking about the value where it's not continuous. We're asking about a different value where it is continuous. We can just plug that number in and get the result. You guys do 5 to 9. Great, second go. Okay, number 5, what do we get? 2. Number 6, what do we get? 0. Cosine of 0 is 1, but 0 squared is 0, so 0 times 1 is 0. What do we get for number 7? 19 halves, yep. 9.5 is fine too. What do we get for number 8? 12, and number 9. Okay, this is the line y equals e. What is e?
It's like -1.
2.7-ish, 2.71. So this is the horizontal line at 2.7181. So what's the limit of e as we approach 4? Yeah. I mean, yeah, 2.7181, whatever. But e is the best answer. Like limit, like y equals pi, horizontal line at pi. So limit at any point would be pi. Okay. This is the same result that we would get like if it was 2, it would just be 2. It's just whatever number it was. Okay, number 8, another example of a function that's not continuous. Number 8 has a vertical asymptote at x equals 3. Are we asking about x equals 3? No, we're asking about x equals 4. So there's no problem with us plugging in 4 and getting that value there. The function is continuous at x equals 4. Not at x equals 3, but it is at x equals 4. Okay. Next two questions here. Draw the graph of a function f such that the limit does not exist at these values. So I've got 3 x values, and I need to draw a graph of a function where the limit does not exist there. Okay.
Sorry, this is just back to the ones like 8 and 4. Isn't it always going to be we're only going to have to plug in the x about for the numerator? Like, is it always going to be ones like that where it doesn't matter like about like where the ASCII goes are? Like,
Well, no, I mean, so number 8, like, it does matter where the asymptote is. The asymptote's at 4. Or sorry, the asymptote's at 3, which is why it's okay to plug in 4.
okay.
If I plug in 3, I'm going to get 9 over 0.
Yeah.
And I'm going to say, like, oh, the limit does not exist. Because that's an undefined value. The next group of examples, when we plug them in, we're going to get different things. It's not going to be as easy as getting a y equivalent. Yeah. Okay. So for this picture of the graph here, if we want the limit to not exist at 1, 2, and 3, what are some things I could have at 1, 2, and 3? Okay, yeah, we could jump. Limit does not exist at 1. What else do we have? Asymptotes. Yes. We could have asymptotes. Anything else? What could I do at 3?
Does it have to exist at 4?
Yes. Well, it doesn't say that necessarily. What was your thought? Like down there?
Or it would be like the the half parabola,
Mm-hmm.
to the side is just like a negative version of that. That'd be
Like this?
negative. Which one that makes it go to the other side?
Oh, yeah. Okay. Yes. Yeah. Yes. This graph here, the half parabola going to the other side, the limit does not exist at 1, 2, or 3 because the graph doesn't exist there. Yes, exactly right. That's the other way that we could make the limit not exist. Yep. If we're saying the limit needs to exist at all the other points, then we can't do that. But very, very good insight there. That's exactly what I was getting at. Okay, so let's say we need the limit to exist at all the other points. So we could have asymptotes and we could have jumps, and that's it. We can have asymptotes and jumps. And now the limit does not exist at any of those points. Okay, so you guys do the same for number 11. Make a graph where the limit does not exist at -2, 0, and 2, but does exist at every other point. Okay, so questions on how to do this? I have basically 2 options of things I can do. What are they? What are the 2 options of things I can put at these points? Jump or asymptote, exactly. So infinite number of answers here. Just need jumps and asymptotes in whatever accommodation we want. Okay. All right, so let's go to the next page. Here's where things get a little trickier. A little more complicated. So sometimes the point that we're trying to plug in, the function's not continuous there. And here's what that could look like. For number 1 here, if I plug 3 into this function, I get 9 minus 3 minus 6. What does that equal? 0. And on the bottom, I get 3 minus 3, which is 0. Oh, nuts. What does 0 over 0 equal?
Isn't it defined?
No.
4.
No.
5.
No. Actually, yes. In this case, it does equal 5. Yeah. Not always, though. But in this case, it does. So here's the thing. 0 over 0 is something called the indeterminate form. What does the word indeterminate mean? Yeah, you can't determine it, right? We can't figure it out. So it basically means we don't know. We don't know what it equals. All right. So here's what we have to do whenever we get 0 over 0, or infinity over infinity. That's less common. We need to, classic math maneuver here, factor the top.
So.
Okay, when we factor the top, what's going to happen? Yeah, we're going to cross off the x minus 3, which means that we have what in the graph? A hole. And the limit exists at a hole? Always, sometimes, never? The limit always exists at a hole in the graph. The limit always exists, and it's just the y-coordinate of the hole. So here's what we do. We've crossed it off. That means there's a hole in the graph. We are left with this remaining part, which is just x plus 2. We can plug 3 into that part, right there, the leftover. When we plug 3 in, what do we get? 5. Told you it was 5. Okay. So, again, when we plug it into the beginning, we get 0 over 0. That usually means there's a hole in the graph. The limit does exist at a hole in the graph. The way we find it is, one of our methods is factoring. Cross off the repeated factor, plug that value into the leftover piece. Okay, so the answer is 5, but I just want to make a connection here to earlier on in the year. Earlier in the year, we had to graph things like this. What this looks like, the line is, it looks like the line x plus 2, which, what are some features of the line x plus 2? Y-intercept of 2, slope of 1, yeah, okay. So, that's not quite a slope. This line basically looks like this, except at x equals 3, there's a hole in the graph at the point 3,5. That's what this graph looks like. But the limit, again, would just be that y-coordinate of 5. Graph size. Okay, so that's one strategy we have, is to factor, cancel out repeated things. Let's take a look at number 4. Number 4, what's going to happen when we plug in 4 for x? What does that equal? 0 over 0. Okay, nuts. All right, so again, 0 over 0, indeterminate form. We have to do something to simplify this. We can't just plug in 4 and get an answer here. What could we do to simplify that? Huh? You cannot square the top and the bottom of a fraction because that changes the value of the fraction. Like if I square 3/4, like I just square the top and bottom, suddenly it's 9/16. This is 0.75. This is like 0.5 something. So yeah, it changes the number. Yeah, not allowed to do that. Good idea though. Other ideas on how we can simplify this? Okay. Is that? Yeah. You want to write with this thing?
Huh?
You want to write with this?
Yes.
Ooh, okay, I like that. So here's what we just got.
There. Student observation.
You're fine. Okay, so here's what Brandon did. Does anyone see what he did on the top there? He changed the top. He factored the top using difference of squares. Yes. Okay, so this, I would say, this is how I like to do it. This is a less common way to do it. You can factor this using difference of squares. That factor will cancel out. We'll just be left with root x plus 2 on the top. We can then plug in 4 to do that. That method, as much as I like it, and I do really like it, will not work for number 2. But I mean, I absolutely would do that. I think that's easier than doing this other thing. It just doesn't work as often. The strategy is basically the reverse of this right here. And this is something that you guys were taught last year when you had radicals in the denominator and had to get them out, is you multiply by what's called the conjugates. Yes. Which is the same thing, but with the sign in the middle changed. This is basically the exact opposite of what Brandon just did, is I'm creating difference of squares on the bottom, right there. So, for example, we did this earlier on in the year. We had a, like if you had the, 3 minus I, the conjugate would be 3 plus I. Yeah, we always see those imaginary roots come in what are called conjugate pairs. But in general, like if I have x plus 3, what would the conjugate of x plus 3 be? Conjugate of x plus 3? X minus 3. Conjugate of x minus 4? X plus 4. Conjugate of 2x plus 3? 2x minus 3. Okay. Conjugate pairs basically make, not basically, they make difference of squares. These are useful because we can FOIL them very quickly. Like, what's x plus 3 times x minus 3 equal? X squared minus 9. Yeah, it's difference of squares. What's x minus 4 times x plus 4? Yeah, x squared minus 16. So it's the first thing squared minus the second thing squared. So 2x plus 3 times 2x minus 3. 4x squared minus 9. Yeah. So we do this because we can multiply it very quickly. So when we have root x minus 2, root x plus 2, it's going to be the first thing squared, which is x, minus the second thing squared. And so we're basically doing reverse difference of squares on the bottom. Like I said, it's exactly what Brandon did, but backwards. Okay, so we have the x minus 4. Now listen, you could FOIL this, but it just is going to take longer. We want to just do difference of squares. Same thing on top. I could FOIL this, or I could notice, oh, those are going to cancel out, which means we have a hole in this graph at x equals 4. Now we can plug in x. Now we can get our loop. Okay. So, number 2, slightly more complicated version of this. Again, if I plug in 0 for x, I'm going to get 0 over 0. But we can use multiplying by the conjugate to simplify this. What would the conjugate be that we want to multiply by in this? It's not going to be x. It's not going to be the conjugate at the bottom. It's going to be the conjugate at the top. It's not going to be the conjugate at the bottom. It's going to be the conjugate at the top. Well, think about it. Do we switch both signs normally? Or do we just switch the sign in the middle? Switch the sign in the middle. Okay, what's the sign in the middle? Yeah. So it's going to be this. Again, we could FOIL the top, or we know it's difference of squares, so it's the first thing squared. This is the first thing. What's that squared? X plus 1. And the second thing squared. That's the second thing. Minus 1. On the bottom, we just do this. We don't distribute. We leave it separate. Because what does the top simplify to? Yeah. And then what's going to happen? And now we can plug in 0 and we get 1. Okay, so we got factoring, we got multiplying by the conjugates. What are we going to do in number 3? If I plug in 1, I get 0 over 0. Yeah. All right, so here's something we are going to want to remember from last year. We got difference of cubes, sum of cubes. So we can actually factor this. Here, our difference of cubes and sum of cubes formula. This is where the acronym SOAP comes from. If you remember that from last year. I don't think it's a very helpful acronym, but with the same sign, opposite sign, last one's always positive. Same, opposite, always positive. I don't think it's very helpful because it doesn't tell you what it's for. But that's what it's for. It's for factoring difference of cubes and sum of cubes. Here. Oh. Okay, number 7. We've got a piecewise function here. We're looking to see what the limit as x approaches 3 is. 3, notice, is where the function changes from one to the other. So what am I really asking in this question? there an asymptote? Okay, if there's a jump or not. Yes, exactly. Because we're in a piecewise function, we're asking, is there a jump? Because if there is a jump, then the limit does not exist. If there's no jump, if the function is continuous, then the limit's just going to be the y-coordinate. How do we figure out if there's a jump discontinuity in a piecewise function? Yeah, we're just going to take 3 and plug it in to both sides. Plug 3 in over here, I get 9. Plug 3 in over here, I get 14. Is there a jump? Yes, there is. So the limit as x approaches 3. Sorry, answer. Does not exist. The limit does not exist. Okay. We can also find limits from a graph with something like this. The way that limits work, welcome back. The way that limits work when functions are added together is we can take the separate limits and add them together. So this is the property of limits that we'll go into more in calculus next year. But we can split those limits up and add them together. So for f of x right here, what is the limit as x approaches 2? 1. Again, that point does not matter for limits, it's just what the graph is approaching. For g of x, what is the limit as x approaches 2? 3. So 1 plus 3. Okay. So we can just find the limits separately and add them together. So that can be easy. Okay. We're going to look at one more example, and then there's 2 other things I'm going to have you guys write down. Our last example is on the back page. The last one. Just FYI, if I was going to do number 8, I would be multiplying this by 2 plus 4 plus root x. 2 plus root 4 plus x. By the way, that would be the conjugate. That's what it would equal. Okay. Number 10. What happens if I plug in 2? Get 0 over 0. Okay. So obviously we have to do something with number 10. Ideas. Okay, we can factor the bottom. How does the bottom factor? It's minus 2x plus 2. Okay. Oops. If I plug in 2, I still get 0 over 0. Ideas on how to keep simplifying this. Multiply the top by x. Multiply x squared. Okay, so one way I could do this, I could change 1 to x over x to find a common denominator. Or I could multiply all of this by x and all of this by x. Either way is fine. I'll get the same thing. Which one were you thinking, Eric? This one here? Okay. So we multiply the top by x, multiply the bottom by x. We're allowed to do that because x over x equals 1. When we distribute x on top, what do we get? X minus 2. Yeah, because the x times 1 is x. The x's cancel on the second one. And then on the bottom, we just get x times x minus 2 times x plus 2. What can we do now? Eric suggested we multiply the top and bottom by x. I think, not to put words in your mouth, Eric, but I think he was thinking he wanted to cancel out that x on the bottom of the 2 right there. Another way that we could get to this same point here is we could find a common denominator. On the top and bottom, we could change this to x over x. We could multiply this one by x over x to give everything the same denominator. And then once everything has the same denominator, we can cancel out the denominators. So that's just another way that we could get to the same result. It's actually doing the same thing. Okay, so we get here. What would our next step be? Yeah, x minus 2 cancels out. And now we can plug in 2 to that remaining part. Okay. So, factoring, common denominators, multiply by the conjugate. Strategies to use when you get 0 over 0 in order to simplify something. Our goal being to eliminate a repeated factor where there's going to be a hole in the graph and find the limit at that point. On the page right before this, at the very bottom right there, 2 special trigonometric limits. We're not going to do very much of this year, but next year we will. What is sine of 0? What's the y-coordinate at 0? Zero, right? Sine of 0 is 0. What's cosine of 0? 1. Cosine is x, sine is y. Here's 0, right there. There's cosine. There's sine. So if I plug in 0, again, I get 0 over 0 for this sine x over x, for this first one here. We can't factor sine of x. There's no conjugate. There's no way we can get a common denominator. This one is one that we can discover by looking at the graph, but it equals 1. The graph of this function basically just looks like, oh shoot, I just graphed it yesterday. It looks like this. And it's just at 1. So you can look at the graph and see on a graph calculator. And then same problem with 1 minus cosine x. If I plug in 0, it's 1 minus 1, which is 0, divided by 0. Again, you can't factor this. There's no conjugate, there's no common denominator. The graph of this kind of looks like that. Not exactly, but a little bit like that. What would we say the limit as x approaches 0 is, looking at that graph? Here's the graph. As x approaches 0, what's our limit? 0. Yep. There's actually a hole in the graph at 0. But that's the limit. So again, these are 2 special trig limits. You're going to use them next year a lot. There might be a couple homework questions about them, but wanted you guys to see.